We are going to study about the magnification produced by the mirror. Technologically, we say it linear magnification, as we want to know that how much the size of image gets changed when we get it to a mirror. It is denoted by the small letter m, and it is defined as the ratio of the height of the image to the height of the object. Here, I is the size of image or the height of image, and O is the size of object. So here we want to find out the relationship for the linear magnification. So let's go through a mathematical derivation. Here we have a figure in which a concave mirror is shown. The object AB is here beyond C. In this case, we'll get a real image of the object which is inverted. We have taken the two rays for the purpose, and the one ray which falls on the pole and get reflected with the same angle as the incidence angle. That is why here angle APB is same as the angle APB'. When we take the second ray which passes from the center of curvature, then it's normally incidence on the mirror and it gets reflected back on the same path. We say that these two rays will meet at a point, that is the B' point. Here we'll get the image A' and B'. So in this diagram we want to find out the expression for the linear magnification. So our first case is for the real image. As we know that the real image is inverted also. So here A', B' is the corresponding image of the object AB. As we can see in this figure, if we compare the triangles A, B, P and triangle A', P', P, we can easily see that because of the same angles, these two triangles are the similar triangles. So using their similarity, we can write A', B' upon AB is equals to PA' upon PA. You can clearly see here that A', B' is the size of image and AB is the size of object. So we can write here A', B' is equals to I image size, but as it is downwards from the principal axis, that's why according to sign convention it should be taken negative, and the size of object as it is upward from the principal axis, that's why it should be taken positive. And PA' is the distance of the image from the pole, that's why it should be denoted by small v, but it is also negative as we are going in the direction opposite to the incident ray. Again, if we talk about PA, then this is the distance of the object from the pole, that's why it is denoted by the small letter u, and it is also negative. When we put these four values in this relationship, we can see that we get the ratio minus I by O is equal to minus V upon minus U. If we further simplify this relationship, we'll get it I by O is equals to minus V upon u. As we have defined the magnification as ratio of the height of image to the height of object, that's why here we get the relationship for magnification in the terms of the distances of object and image from the pole, and it is equal to m is equal to negative of v by u. It is for the virtual image. We want to see that if the image we obtained is virtual, then the relationship of magnification and object and image distances changes or not. So here in this diagram you can see our object is AB here, and we have taken again the two rays, one which falls parallel to the principal axis on the surface of concave mirror and reflects such that it passes through the focus, and the one ray is which falls on the pole and gets reflected. Here, by the laws of reflection, these two angles should be similar, and as this angle and this angle shares the vertical opposite pair, thus this angle should be same as this angle. That's why again on comparing the triangles ABP and triangle A-B-P, we find that these two triangles are similar. So here, by the similarity of the two triangles, that is triangle ABP and triangle A-B-P, we can write A-B upon AB is equals to PA upon PA. Here, as both the object and the image are upside from the principal axis, that's why both are taken positive here like this. And if we talk about the distance PA that is this distance, it should be taken positive, that is V, and object distance is always negative. As for to take it, we move in the direction opposite to the incident ray. That's why we get the ratio I by O is equivalent to minus of V by U again. So here again we get the relationship among the three quantities linear magnification, object distance and image distance as m is equals to minus of V by U for the mirrors. You can also derive this relationship for convex mirror. Now we want to find some another formulas for the magnification. As we have the mirror formula which says 1 by U plus 1 by V is equal to 1 by F. If we multiply both sides by U, then we get the relationship as 1 plus U upon V is equals to U upon F. And again, if we rearrange this equation, then we find out U by V is equal to U by F minus 1. If we further solve this equation, then we'll find U upon V is equal to U minus F upon F. And as the magnification formula says, m is equals to minus V by U, that is small m, that is linear magnification, is equal to minus V upon U. So here, for taking this equation in the form of linear magnification, we'll give it the form V by U minus is equals to F upon F minus U. So here we have another formula which can be used to take out the linear magnification produced by the mirror. Also, for this case, and we have another case. Here, if we multiply the mirror formula by V, that is the image distance, we can get it as V upon U plus 1 is equal to V by F. Rearranging this equation, we'll get V by U is equal to V by F minus 1, and for getting it in form of magnification, we'll give it the form minus V upon U is equal to F minus V upon F. And here we are with the another form of the relationship between magnification and the focal length and the image distance. So we should take a problem, and the problem says that we have to find the position of the object which is placed in front of a convex mirror, and its focal length is given to be 20 centimeter, and it is given that the image is produced, which is in nature is virtual, and it is half the size of the object. That's why if we want to get the solution for the problem, we are given the hint that the magnification, that is the ratio of the image size and the object size, is half. That is, if we take it in the terms of U and V, then we'll find out that minus V upon U is equal to 1 by 2, and it implies V is equal to minus U upon 2. So here the relationship between image distance and object distance, that it is the half and in the opposite side of the mirror. So in the mirror formula, that is 1 by U plus 1 by V is equal to 1 by F. If we put the values, then so here on putting the values, we'll get 1 by U minus 2 by U is equal to 1 by 20, and then it implies U is equal to minus 20 centimeter. So by using the mirror formula and the magnification formula, we get the object distance which is equivalent to 20 centimeter.